Today I'll talk about some work I've been doing as a side project that started back in, I think, sometime November at a Xerox PARC meetup in San Francisco. It was my first time kind of experimenting with the Halo2 in the Halo2 ecosystem. I'm Max Gillett. I'm an independent developer and I guess investor in the crypto space. And yeah, this work will specifically about the verification component in Halo2. So yeah, just to give some motivation, right? Why implement FRI in Halo2? It's already available in some other proving systems like Plonky2. I think one good reason is that the Halo2 constraint system is general enough to be targeted to other backends. So in some sense, once we write this chip, we don't have to use the Halo2 IOP. We can, or even we can switch to some multilinear extension, and I think another main reason, something that was motivating me from the beginning, is that we can compose. If we have a FRI verification chip, we can start composing with other proving systems. For example, this is a key component in the verification of a Stark, verifying a Stark. And so that could be used to reduce the on-chain, verification costs of proving these other kind of more expensive proofs. And then I think a third motivation is just that I think there's a good argument that moving to FRI and specifically Goldilocks will result in faster recursion for the Halo2 IOP if you switch out the polynomial commitment scheme to FRI. So just a sort of brief outline of the talk. I'll start with just an overview of the FRI protocol. Then this is going to be pretty high level. I'll talk about a few interesting details about the chip that I found interesting about the chip implementation. Then some benchmarks for both the BN256 scalar field and the Goldilocks extension field, and some future optimizations that should be made. So just before I begin, these are, I think, some resources, some of which I found helpful in understanding sort of the deeper theory behind FRI. I don't think that's within the scope of this talk, so I'm just kind of including this slide. At a really high level, FRI is an actual polynomial IOP in itself. There's a back and forth between a prover and verifier. It asserts that a committed polynomial is within some given degree bound. The polynomial commitment is actually coming from just a Merkle tree commitment. The FRI IOP is what gives you a statement about the degree bound of those claimed polynomial evaluations. And also at a high level, which I'll then go into next, FRI can be broken down into a commit phase and a query phase. And the sort of artifacts of a FRI proof are various steps during the commit and query phase. To sort of illustrate how the commit phase works, I've sort of outlined three columns here: polynomial evaluations, the polynomial itself, and then the domain that the evaluations are over. So if we just consider some polynomial that we want to make a commitment to, and claim has a certain degree, we first split sorry. Yeah, we first evaluate this polynomial over a domain that's larger than the degree of the polynomial, and the domain should be a power of 2. So here, omega is a generator of basically a subgroup of large power of 2. So the field has to have high two-adicity, and right, the evaluations are just f sub 1, evaluated over elements of this subgroup. It's a multiplicative subgroup. So if we split the polynomial into 2 parts, even coefficients and odd coefficients, we can then construct a new polynomial, f2, that has half the degree. We've changed, I don't think you can see my cursor, but we've substituted, just some verifier randomness. It's just a field element alpha. And so, right, each F1 even, F1 odd, they both have half the degree of F1. And so we're summing together 2 polynomials that are a random linear combination of 2 polynomials that have half the degree. So we then evaluate F2 on a domain half the size, right, just the square of the previous domain's generator. We now end up with a second layer of evaluations of F2 that's half the size. And we can continue on, construct a third layer that's half the size, and so on. I mean, we can continue this process until we get down to just a single evaluation, or we can stop at an earlier layer if we want. So just some notes about that. Right, the committed polynomial, that f, like the statement we're making is that has half the degree. It's at least smaller than half the degree of the initial domain, the evaluation domain. It's important to note that this folding procedure that I described, right, this like summing of the even and odd polynomials, like this respects the degree. So the degree of each polynomial is halved as we go down layers. And right, like I mentioned, we can stop prematurely if we want, if we just want to claim that maybe some polynomial and some, nth layer has some degree. It doesn't need to be a constant. So yeah, hopefully that's clear. The next phase, right, so the first phase, we constructed a bunch of layer evaluations. We also did a bunch of hashing to commit to, each layer. That'll become clear why in a second. So in the query phase, what we're doing, again, this is still sort of the responsibility of the prover. There's a position drawn. So in this case, the second element of the first layer, we start with the first layer. There's then a folding process within the layer where we add half the domain, half the size of the domain of the set of the next layer. And then if it is sort of larger than the domain of the layer we're on, I mean, we're gonna have to do modulo like the size of the second layer. I'll revisit this kind of at a later slide, and I think if it's confusing, it'll maybe become clear then. But we then interpolate both of these evaluations. In this case, I mean, in general, it's a Lagrange interpolation. In this case, it's just sort of a line. We then draw some verifier randomness. Usually, we use some kind of function of the layer of the commitment to the layers. So C here is the commitment to the polynomial evaluations in layer one. So we draw some verified randomness, and then we evaluate this interpolated polynomial. In this case, this line, we just pick a point evaluated alpha one, and basically due to the properties of what I showed during the commitment phase, like the summing, like the representation of the even and odd polynomials over this subgroup, it turns out, if you work through the math, that this evaluation at alpha one corresponds to, in this case, the second element in layer two. So, right, what's going on here is like the prover commits to a bunch of layers, and then right, draws a position and sort of proves that they've done the folding correctly. And so this is from layer one to layer two. We can again repeat this process, like fold the position in layer two, and then again interpolate evaluated alpha two, and sort of compare with the point in layer three. And so, yeah, this yeah, so let's see. Yeah, I mean, I'll maybe come back to some of these points, but the folding factor, right? There's no reason it has to be. Yeah, is there something else I want to say here? Yeah, I mean, so, right, like, you might maybe wonder, like, why, I guess you have to do the query phase if the prover's already kind of done all this folding and done this work. And I guess the answer to that is that, like, at the end of the day, we don't want to have to send like all the evaluations to the verifier. We just want something that's exponentially smaller. And so this query phase is sort of producing like the Merkle proofs, like is sort of generating positions, evaluations, authentication paths to those evaluations, and passing, like kind of outputting that in a proof that's then given to the verifier. So this procedure, right, is done for each layer, and then it can be repeated multiple times to increase soundness. So typically you're doing like 20, something in the order like 20 to 50 independent queries. So yeah, hopefully that's clear.
For a single evaluation proof.
For single FRI proof.
So like the query, like what's the like interface of a query phase? Like what are we trying? Are we trying to prove that the committed polynomial evaluates to Y1 at that corresponding root of unity?
Yeah, we're trying to prove that these three evaluations are sort of collinear. Like the two evaluations in kind of layer n, and then a single evaluation in layer n plus one.
In order to prove that the folding scheme is done correctly?
Yeah, so I mean, if we just stopped with the commit phase, we'd have to send like all the work to the verifier.
Right.
In which case there would be no cost savings there. This is a procedure to basically like check that the commit phase was done correctly, that this folding scheme was done correctly, while only sampling like a very small number of elements. So like the query phase is like duplicate work in some sense by the prover, but it's like negligible compared to the commit phase.
And so you're saying in order to assert that the folding scheme is done correctly, you have to do this multiple times for like multiple Y1s, like you do the Y2 or something?
Yeah, so this, like in layer two, like are you talking about stepping through multiple layers, like in a single
Well, you said for the increased soundness, you do this many times.
Yeah,
So
so
what do you change in between each of those?
you're drawing just new positions, that's all.
So instead of Y1, you do it for Y3 and
Exactly,
Y5.
yeah.
Right, okay. And this is all to assert that the folding is done correct.
Yeah, exactly. And yeah, the verifier at the end of the day only sees sort of the evaluations, like the Merkle commitments, the Merkle proofs, like the evaluations of the positions that were drawn. And like their folded equivalents at each layer. Yep. So yeah, I mean, one other like side point here is just you don't have to, like, here the folding is just picking one other element in the layer. There's actually a procedure. I mean, it's easy to generalize this to larger powers of 2. So we can fold 4 times, 8 times, 16 times within each layer, and that will, each additional folding factor will basically have the number of layers that we need to generate. So previously I was just having, this is dividing each layer by 4, the size of the layer. So this can save you, it can save downstream with the verifier computation. But yeah, as I mentioned, it can be repeated an arbitrary number of times. There's sort of like, yeah, this is a separate issue, but you can again consult like those resources if you want to see the exact how this relates to soundness. And like I mentioned before, like we don't need to go down to just a single constant. We can stop at an earlier layer and basically convert those evaluations back into a polynomial, just interpolate and then check that the degree is actually what's claimed. If the prover if the prover was honest, then it's sort of guaranteed that that polynomial is going to be smaller than the allowed degree. Hopefully that's clear. That I think I'll also come back to that later. But yeah, I'll switch gears now. I guess if there are other questions about, I can also come back to it at the end of the talk, just about the protocol. Yeah, maybe we can say that for the end of the talk. But so, yeah, in terms of the implementation for the verifier, I wanted to make this generic over the base field, the extension field. So in the case of Goldilocks, like FRI, the soundness would be 64 bits, which is sort of insufficient. So I've used a quadratic extension, gives you a maximum of 128 bits. I've also made this generic over the random coin sort of procedure. So how we actually generate alpha, or the verifier supplied randomness, and also the hash function. I'm not making any assumptions about whether this is Poseidon or something else. So I've also packaged the library with a sort of testing suite that parses Winterfeld generated FRI proofs into the proper form. I think a nice thing in the future would be to also add support for Plonky2 generated FRI proofs. But yeah, I didn't rewrite, the FRI proving process, and I don't think there's really a need to right now. And the chip also makes like very heavy use of axioms, Halo2 lib, Halo2 library. So this is basically I'm not using any custom gates at all in the chip at the moment. There's just a single vertical Planck gate. And within that Halo2 lib, right, I'm just importing a single like range and flex gate chip. And so this is something provided by Axiom and essentially implements almost all the numeric and sort of control flow operations that it needs. So things like inner product or selecting, and I've just had to extend it slightly to allow for like extension field operations, but it's sort of trivial. Although those could be, I think, more optimized. And yeah, another sort of maybe unique thing is that, right, I'm making use of this library. I'm only doing a single pass, only have a single pass layouter in a single region. There's not like multiple regions defined for each chip, and I think empirically that sort of helps with proving time. But yeah, so again, really high level protocol. I'm not sure it'll be that useful, but just sort of a summary of what I've discussed. I'm just going to focus on a few of these steps, right? So we, at the very beginning, we just want to the verifier randomness from the committed layers. And then for each query, we need to figure out the coordinate of the provided evaluation. We then want to do some colinearity check, right, between successive layers, successive layer evaluations, authenticate the Merkle proofs, check that the claimed remainder is equal to the kind of final valuation. I mean, there's about 7 steps here, I think. Not many of them are really that interesting. Like, I guess I just want to zoom in on like steps 3, 4, and 7. So steps 3 and 4 sort of make use of a bitwise or bit decomposition of the position. And then step 7 makes use of sort of an argument comparing polynomial evaluation and two evaluations of a polynomial, one in a coefficient presentation and one in an evaluation representation, in order to try to save work. So just the colinearity check, right? It might be sort of too much detail over this talk, but right, an artifact of the proof is essentially a Merkle commitment to a tree of layer evaluations. We have one Merkle tree for each layer, and in the proof, we're just given individual leaves and paths through this tree, and the leaves are organized by position and any folding done within that layer. So, right, thinking back to like the first few slides I showed, like one leaf would just be, I think it was position 2 and position 9, those 2 evaluations. And so, right, if we just want to check that like the evaluations and for a given query, the evaluations in one layer sort of match those in the second layer, what we're doing is, for example, we take this, let's say we drew position 0. We would look at this first leaf that was provided to us, interpolate between omega 0, omega 4, those are the 2 kind of x coordinates here, and then evaluated alpha. That gives us z0, which should be the first leaf in the next in the Merkle tree for the next layer. So I mean, one sort of nuance, I guess, about this is that depending on where we draw, what position we draw, right, we can either be in the first or second half of the domain. And so, right, if we're in the first half, like when we fold, for example, we derive y9, but if we started with y sub 9, when we fold, we actually have to wrap around and the folded position within that layer is going to be y sub 1. So, I mean, I guess an insight here is that we don't actually need to like compute. It might be nasty to do like sort of modular arithmetic. This way, we don't actually need to compute the folded positions to verify things. We only need to compute the correct ordering. And so if we just look at like a single position, let's say like 141, this is actually greater than half. Let's say we're in a domain size of 256. So we're folding, the next layer should be 128. The folded position, the computation here is just 141 plus, the size of the domain for the next layer, and then modulo like the current domain size. And so this would give us 13. If you look at the bitwise decomposition, I mean, this is sort of like easy to see. Basically, the ones bit, the highest kind of bit here corresponds to 128. And so obviously, if we're adding, 1 to that bit, it's going to overflow into the next bit. And because things are done modulo 256, that bit is basically eliminated. So this would tell us that, right, we need to swap basically these evaluations that were given to us. So hopefully that makes sense. I mean, this is also the case for, right, you don't need to swap if you drew something less than 128. That 128 bit is now going to flip from 0 to 1. So I think, I mean, another nice thing about this like position bit decomposition is that we can also reuse it for the next step 4. Right, so if we just want to derive, like we're for each evaluation, for each set of like folded evaluations within a layer, we also have a Merkle path, a Merkle proof, and we need to authenticate that. But right, the prover could, like, we need to know sort of what index this corresponds to, otherwise the prover could maybe lie about it. And so it turns out we can just reuse this position decomposition, and basically, like in the smallest bit here, like 1 would tell us to choose, the right sibling, 0 would tell us to choose the left sibling. And because, each time we fold, we're basically just setting a bit to 0, leftmost bit to 0. I mean, we don't have to like reorder or recompute bits here. We're basically just slicing successively smaller bits. So yeah, this, I mean, I don't know, this is a huge cost savings in the grand scheme of things. Like this doesn't matter, which I'll get to in a moment, but it is like a sort of optimization that can be made. And then I think this is also interesting. This is an argument that I think is sort of inspired from like this MTT argument that Remco had made, and Al from Polygon Mine like articulated this in the GitHub issue referenced. So basically the process here, right, like naively, if we just want to check that some evaluation like has some claim degree, we do some, Lagrange interpolation. It would be order n squared. A way around that is to first non-deterministically compute the coefficient representation, draw some verifier randomness, and then basically compare evaluations between the evaluation and coefficient representation of those two polynomials. And so Horner evaluation, right, of just the the coefficients is going to be linear. There's this barycentric Lagrange evaluation that sort of this pre-processing can be done outside of the circuit, and that can be like within the circuit, you just have an order n evaluation. I put a little asterisk here because in the actual circuit right now, I haven't implemented like this inversion that's necessary for this. So it's actually just plain Lagrange evaluation and doing it's like order n squared and kind of adding completely unnecessary overhead, but it's very simple to switch that. But again, as I'll come to, this is actually doesn't turn out to be a source of like overhead in the proof verification. But yeah, once you check that these both valuations are equal, I mean, you then can go back to your non-deterministically generated coefficient representation and just check that it has the correct degree by counting, zeros. So yeah, that's clear. I think the next sort of final part is just benchmarking. So I've implemented so far just BN256 and Goldilocks and a quadratic extension field. So I'll start with just BN256. So the hash function here is not optimized, or there's no custom gates, no lookup tables. Like it's just this is all just like Planck gates, but it comes out to be about 2,500 trace cells per sort of merge hash function call. If we look at just the verification for the entire chip for 28 FRI queries, we can look at this by log domain size, which is just the, right, thinking back to the first few slides, like just the number of elements that we evaluated this polynomial over. So 2 to the 10 for this first row, which I think is 1024, and then the remainder degree is basically indicating at which layer we sort of stop at. So I think this is stopping, maybe like 5 or 6 layers sort of before that, the final layer for R equals 32. So we can see that, for a given row, like, which makes sense as we sort of shave off additional layers, we have to do less hashing. And it also makes sense that as we increase the domain size, right, we're increasing the Merkle authentication path length. That's the only area that the domain size actually influences the verification, right? We have a much larger, like, vector of leaf elements to commit to now, so we have a larger depth. And so it makes sense that as we increase the domain size, we also increase the number of hashing that needs to be done, and things get more expensive. But if you actually just, sort of do a computation of 28 queries and then like, however many layers are dictated by the remainder degree, and then however many, for each layer we need to do, this many Merkle authentication paths according to domain size, like you can actually compute these numbers like almost exactly from the hash function multiplied by, these 3 parameters. Yeah.
Sorry, quick question. If you use higher powers for the folding, would that also affect the tree depth here, or?
Yeah, it would. Yeah, so that would come in. That basically just for each time you like each additional power of 2, you're gonna like have the number of layers you have. So that'll reduce the hashing. Yeah, that'll reduce the hashing, and I'm sort of working on that. I mean, it's sort of the trivial thing to add. There's another optimization which I'll describe, is you don't actually have to compute like all the way up to the root of the tree. You can stop at kind of an earlier depth at all. Yeah, I'll reuse that. But to answer your question, yeah, it's this will reduce the number of hashing simply in that you have to do fewer. Right, I mean, they're just fewer evaluations to authenticate.
I have a question.
Yeah.
That. Is there a drawback using powers of two?
So the drawback is like this like colinearity check that I described is now a Lagrange interpolation over like however many elements your folding factor is. So there's some cost from that, but like empirically that I've seen that cost is like incredibly low, especially if you yeah, I mean, I don't think you even need to use this like this argument I described like for step 7. So I think, yeah, there's not really a major drawback. I'm sure there's like, if you optimize this, there's some point at which it becomes like sort of not worth it. But yeah, I think like these costs would come down like tremendously with larger folding factors. Yeah, and so the proving time, just with the Halo2 PSC fork, is, I mean, this depends on like different parameters, like how many rows you're kind of working with, but for the upper right entry in this table, it's about 1.5 seconds, and it doesn't really, I mean, this is like a completely orthogonal issue from like proving time is just trace cells. I mean, I'm not using any like custom gates here, so it's just a function of like the Planck, how many times you're, how many trace cells you're using, and the layout of the table or layout of the trace. So yeah, Goldilocks, not great. I mean, my implementation, which is like somewhat buggy, there's like, I'm not getting perfect agreement for some hashes, is like almost 8 times that of the BN2F6 hash. I mean, this is coming mainly from the fact that like we don't just have one field element now, we have 4 field elements for each like representing each hash digest. But my understanding is that there are like much more efficient implementations of Poseidon that could be using here with lookup tables. Again, the verification cell count for 20 queries, I mean, it's about 8 times that of BN2F6. And again, like it sort of scales how you would expect. And I think like major speed ups would come from like the folding factor, better, you know, hash function implementation. And yeah, I mean, this is this could come down like, I think potentially a couple orders of magnitude or more.
And so therefore, you need 4 elements because Goldilocks is 64
Yeah.
bit, and you're trying to get the full 256 bit.
Yep.
Do you need to have the 256 bit like hash value?
You're saying like, could you stop with like 128 and just
Or
2 elements?
64, is that, yeah.
I don't. Yeah, I mean, something I've wondered, like the BN2F6 is also like not 256, it's like 254 bits, so it's already slightly lower. I don't know. Yeah, I don't know enough about like the sound, like the sort of soundness arguments to say, but it is something that I think would like be a good direction to explore. I mean, that's some, if you could have that, I mean, I think you. But I think the other problem is that yeah, I mean, it's something to explore. I just don't have like a really good understanding of if it's possible.
But it's like these are comparing to like you're keeping the 256 bit security thing. Cost of between
for the hash function, yeah.
For the hash function.
The security of like of FRI is like sort of the maximum of either like the field size or sorry, the minimum of either the field size or like the number of FRI queries times times like the, which I didn't get into, like the like blow up factor, like the like Reed Solomon encoding that's been done like before FRI. And then also if you're doing like some kind of grinding. So usually it's not like the field size that's an issue, but I think maybe that soundness analysis that I'm referencing like assumes close to like a 256-bit hash function. I just don't know. I don't know enough. Like I said, these numbers are like just very easy to compute from just like heuristically. But yeah, I mean, one interesting thing I haven't really seen like compared a lot is that, right? One interesting question is like, if we actually like can generate both the FRI, like if we have the FRI PCS implement in Halo 2, then we can actually prove using the Goldilocks field. I don't have that work done at the moment, so I can't like estimate the actual proving time for the Goldilocks trace, like, or Goldilocks FRI proof, only like the trace cell count. But multiplication, the Goldilocks field is like over 20 times faster than that. The scalar field on my computer, addition subtraction is 6 times faster, according to Jonathan Long. Like, and you shouldn't quote these numbers that he gave me. These are very rough numbers, but this, we can expect that maybe field arithmetic is for in some cases like up to 93% proving time. And so if you just break that down by the distribution of different operations done, like multiplications, addition, subtraction, you expect, working with these numbers here, about a 15 times speed up, assuming that there's sort of no overhead from like the Merkle hashing that you now have to do in the FRI PCS for the prover. So, right, like there is going to be, assuming you're using 4 field elements to represent like a hash digest during verification, there is going to be like some additional cost with the and the fact that we have a quadratic field extension, and a multiplication is now like 4 cells instead of 4 cells. So there is some additional cost, like trace cell cost, but if the proving time is 15 times smaller, and the trace is just 2 to 4 times larger, I don't think, I think these things like, dramatically offset the increase in trace size. Last thing, to just wrap up, like further improvements, I think in addition to the folding factor, like one thing that's going to really help is not authenticating layer evaluations up to the root. Instead, you can just stop at a lower layer, or I shouldn't say layer, lower depth in this tree, and just supply in the FRI proof sort of a vector of all the internal node hashes at that depth. And so this is something that's like heavily used in the Plonky 2 implementation, I believe, and could also, I think, give at least like an order of magnitude or more speed up. Here, it's also simple to, I think, implement. I just haven't gotten around to it. The first 2 I talked about. The third, I think, I'm not sure how relevant it is, like sort of at lower layers, right? When you start like shrinking the domain size enough, like the positions that are drawn are actually duplicate. A lot of them are duplicates, and so you end up just like re-authenticating, positions that you've already done, and so that's sort of wasted work. Maybe there's a way to avoid doing that by using some kind of lookup table and not having to just pre-commit in the circuit to doing 28 times 20 queries times 10 layers times however many Merkle proofs in the layer.
Max, could you reuse proof branches like you do in multi-proofs, Merkle multi-proofs.
Sorry, can you repeat one more time?
Can you reuse the queries that you've made in the past, similar to how you do Merkle multi-proofs, where adjacent elements kind of share a large part of the proof and save on the total amount that you need to commit in?
Yeah, that's an interesting, I mean, so you could, yeah, you're saying like you could have just leaves encode more than just the folded.
Like just by using the observation that adjacent leaves in a tree share
Yeah.
most of the proof.
Yeah. Yeah, I think that could help. Yeah, I mean, I was imagining like something where if you just shifted like all Merkle authentication to some like dynamic lookup table, like you don't just have to assume, like I could just set some flag where, you know, I've seen this position before, I don't need to sort of re-authenticate it. But I think, yeah, what you're suggesting might also work and not be expensive for these lower layers. But I think this is like potentially just completely unnecessary when you start using like large folding factors, and you also don't need to fold like at a constant folding factor. Like you can sort of you can define like multiple folding factors, and so you don't need to go down to maybe the depths at which, like layer depths at which you're going to have these like repeated positions being drawn. So yeah, I'm just not sure how much of a issue it really is, like on second thought. But yeah, that's it's yeah, I'm happy to take any questions, and you know, it's coming up on the hour.
No questions on Zoom or in person? How do you like working in Halo2?
So I think like with like this like, you know, the stuff that like Jonathan and ye have like written like this Halo2 library, I think it's like a very pleasant experience because I can just call out, you know, whatever instructions I need, and I rarely have to like implement new ones. If that library didn't exist, it'd be very painful just because there would be like a lot of low level work that needs to be done. But I actually felt like more productive than like in some like, you know, domain specific like VM languages. Like I'm not sure actually that like, yeah, I'm not, once I kind of got comfortable with like Halo2, I didn't feel like less productive than like Cairo, for example. Like there's a lot of like different things you need to worry about in Cairo. Like there's no like for loops, and you have to sort of keep track of variables and do like recursion and function recursion. So yeah, it's I think the main pain points were sort of like keeping actually all like dependencies like in agreement, because I was using, you know, like a Poseidon implementation from some package that didn't like reference the same like, you know, finite field library, and like I just had to, I'm trying to make this like sort of like reusable. So ideally like all the changes I'm making get like merged upstream somehow, but it's still just a challenge because everything seems to be using like a different tag or different version of some library. And yeah, I think one nice thing to do, which also like I think Axiom has done like a good job within their library, is like making like enabling features so that you can choose, you know, for example, the PSC fork or like the Axiom fork or like some other fork. I mean, so I think that there's maybe like work that could be done to just like select between the different like you know, people do want to reuse this as like a component, like they can sort of turn
Just
on
to-
like, okay, yeah.
Just to give like some, at least the context of how I experienced this with Bellman. Like there was Bellman, then there was Bellperson, then there was another Bellman fork from Filecoin, and then there was ArcWorks, and now there's a rewrite of ArcWorks, and ArcWorks itself got forked into Zexy. So there's been 10 libraries re-implementing the same traits, and it feels like it's going to be unlikely for us to get people to coalesce around one approach. So it almost feels like we have to sort of lead by example here and like gather people around one library that's the best. And one thing that we could be doing is kind of like look at all the forks and start aggressively upstreaming the most impactful changes. I.e., instead of expecting that the project to just coalesce and accept Roperson there and whatnot, let's just pick one library that we like, and let's start porting over changes from everywhere else.
Do you see that more like, I mean, do you see like coalescing around like just a couple of libraries, or like ArcWorks and Halo2 ecosystem, or like you try
I don't
to
know,
merge those two together, or?
like just as an outsider, like even the fact that we have Axiom Halo, we have PSC Halo, and we have like the Scroll Halo, that's already a big ass problem.
Yeah. Yeah, I think this
Like
might be
Remco is re-implementing stuff all over and over without dependencies. You know, we cannot be doing that. We need to like coalesce somehow, and feels like it's gonna happen. It's not gonna happen organically, and people tend to gather around the best software. So we probably need to like just make them move, either via feature richness, performance, whatever.
Yeah, I mean, it seems like most of the forks within like the Halo ecosystem are coming from like just performance driven and less like sort of specific features that need to be added. So maybe it's kind of easier to, yeah, coalesce there, but I imagine it'd sort of be harder elsewhere where, yeah, there's, I don't know, different backends and things, but yeah, that's a good point. Hopefully that happens. I think there was one chat message. Oh, no, just GM. Yeah, but if there's no other questions, yeah,
Cool.
thanks for your time.
Yeah, thanks a lot for doing this talk and for doing this awesome work. All
Thanks.
right. See you, everybody.